right? Nanomaterials. These nanomaterials you can characterize in a different way, all right? Either nanoparticles, nanotubes, or quantum dots, or nanocapsules, or aerosols, depending on the different schemes, right? Suppose you have a manipulation of shape and structures, right? Spheres, needles, platelets, tubes, you characterize as nanoparticles. And if you have especially polymeric or carbon tubes, right, treated, coated, or core shell, right, you call it as nanotubes. And then especially if you focus this on zero-dimensional particles, right, single particles on a zero-dimensional thing, we call it as quantum dots. And then intentionally or unintentionally you try to manipulate as a capsule, we call nanocapsules. If you put it in a gel-like thing with gases or liquids, ferrofluids, or aerosols, right, we call as aerosols. Okay, so broadly you can characterize the nano particulates or nanomaterials into different categories. Okay, so there are already 2 days lecture has gone. Most of the lectures, I don't know what they discussed, but still I try to give you 1 or 2 slides on that thing. Broadly, right, you have 2 different routes for the synthesis method. Either you have a bottom-up or top-down. In the bottom-up approach, you have a smaller components, right? You built up based on the smaller components into complex assemblies, right? In the top-down, right, you may have a bulk one, and you try to work on it to make it create a nanoscale smaller ones. So making smaller ones as a nano thing, as a improvement of the building blocks is bottom-up. And the bulk ones, which are more than micrometer or millimeter sizes, to bring it down to nanometer assembly, this is a top-down process. This top-down approach often uses fabrication, mainly nanofabrication methods, which I tried to discuss on Friday as a first lecture. And it also uses controllable tools, mainly milling to shape and size the bulk ones. Okay, so broadly, the top-down approaches, right, you can classify methods into ball milling, lithography, inkjet printing, equal angle extrusion, beating, sintering, exfoliation, grinding, and sieving. Except that ball milling, lithography, and inkjet printing, all the other methods are only for namesake methods, but they are all initially tried to prepare nano materials, but the predominant methods which are now used in the top-down approaches are only ball milling, lithography, mainly lithography, and then inkjet printing, usually called 2D or 3D printing using inkjets. Then with the bottom-up approaches, the synthesis methods which are predominantly used by every researcher to prepare nano materials are chemical, self-assembly. This self-assembly you can have in lithography also in self-assembly. Mainly this is a chemical route self-assembly. Then salt gel, a part of salt gel, co-precipitation, hydrothermal, solvothermal, and sonochemical vapor deposition. The vapor deposition we may have either physical or chemical vapor deposition. And then electrode deposition, where you can have electroless or electrochemical deposition. Once you want to have a fibrous route, then you may need a electrospinning process to prepare nanofibers. And then inert gas condensation, wherein you modulate or modify the vacuum deposition processes with 2 different liquid nitrogen chambers to get inert gas condensation. These are all some of the predominant used bottom-up approaches. I have classified some of them. There are many more methods which are coming as modification of these routes, or special routes applicable to new materials. But these top-down and bottom-up approaches are classified mainly by these classifications. Okay. Now I try to go by individual synthesis methods, how one can use it, but I try to give silent examples also, which we did use in our laboratory. Predominantly, we are using bottom-up approaches, but ball milling we do use, but in a limited manner. So I try to discuss mainly on the bottom-up approaches today. Tomorrow, I mean on Friday, on first part, I try to discuss the synthesis by ball milling and lithography. And on Friday, the second part, I try to discuss about the functionalization of different materials, right? For the 3 hours, I try to discuss on synthesis of methods, and then the last 1 hour, on a 4-hour lectures, I try to discuss on the functionalization. Okay. So this is a classic picture which gives you all the methods in a pictorial way, but I'm not going to discuss anything more on this, but I try to go step by step with the particular methods, right? So this picture gives you almost what are the silent features of different methods of bottom-up or top-down approaches. Wet chemical process in the bottom-up approach is the one which has been initially worked by many chemistry researchers, as well as those who wanted to do on synthesis of any metals or metal oxides through chemical routes, and also chalcogenides, metal chalcogenides by chemical routes. It mainly uses 3 different ways, but I try to discuss elaborately on only one, that's a hot injection, which we do use elaborately in our center or in our group. All right. So this chemical route preparation methods of nanoparticles uses reduction reactions mainly by borohydrides or hydrogen, or using alcohols to synthesize metal nanoparticles. Then thermal decomposition of reactants, mainly metal surfactant complexes. This thermal decomposition is carried out by 2 different means. One is a hot injection, the other one is heat up methods. I try to discuss what is hot injection and heat up after the theoretical part for this chemical process. Then, in addition to aqueous medium, non-hydrolytic solvent reactions are also used by this chemical process to prepare oxide and nanocrystals. Right. So there are 3 different ways one can use this chemical process: through reduction reactions, or through thermal decomposition methods, or through non-hydrolytic solvent reactions. Okay, this classic graph you might have seen several times from those who present work on wet chemical process or on nanomaterials. Right. Essentially, this is Oswald ripening process, which was used to explain the nanomaterial developments, right? So, which you can use it to have a size selectivity, as well as to optimize the sizes for a particular dimension, and also to stop the reactions or agglomerations to have a regular uniform sized particles or spheres or whatever dimensions you want. Okay, this is simple 3-neck flask, which is very much used for wet chemical process. I try to explain this also in the subsequent slides when I come to specific preparation of nanomaterials. And this wet chemical process is mainly used for all kinds of metals, semiconductors, especially chalcogenides and oxides. Okay. As I said earlier, surfactant is a necessity for whenever you go for thermal decomposition, when you go beyond these reduction reactions. Right, the surfactant you can have either hydrophilic or hydrophobic, but usually the surfactant head group is hydrophilic and the tail group is hydrophobic, and it tries to give steric stabilization once you make this surfactants in an aqueous or non-aqueous medium. And these surfactants are very much used when you prepare organic or polymeric nanoparticles. These are very, very essential component when you go for any organic or polymeric nanoparticles. And the stabilization for inorganic media, especially for metals, is carried out using electrostatic stabilization, which is explained with the pictogram here, all right, which gives you an absorption of ions to the surfaces and creates a double layer, which results in the Coulombic reflection of individual particles and accommodates these particles within the surfactants so that there is size selectivity and uniform sizes for the nanoparticles. This occurs generally in aqueous media, right? This whole explanation may vary once we go for non-aqueous media, which I try to explain shortly during this presentation. Okay, so the surfactants are very important for synthesizing these nanoparticles because the surfactant stabilizes the nanocrystals by preventing aggregation, and the surfactants have optimum binding capability, right? Not too strong so that it would not allow to grow, and not too weak, right? So it should form aggregates. So the surfactant nature of surfactants, right, should be optimal binding capability to have a size within this nano scale. The additional energy needs to be such allow the dynamic solvation during the growth, also controlled using the control of surfactants. Okay. Mainly alkyl thiols, phosphines, phosphine oxides, phosphates, phosphonates, amides, amines, carboxylic acids. These are all the things which are used as surfactants. These surfactants are exchanged with another coating of organic molecules when you want to have different polarity or different functional goals. These surfactants can be temporarily or easily removed when you want to have an epitaxial layer of another material of different electronic or optical magnetic properties. And so this process that we try to do in our synthesis routes also, we either you call it as exchange, Ligand exchange, or through phase transfer, or there are some other chemical processes wherein we try to change the surfactant or remove the surfactant to have different electronic, optical, or magnetic properties of the nanocrystals or nanoparticles. And also, you can have core shell structures using these surfactants very easily. And this core shell concept also I did explain during the course of this lecture. And by controlling the mixture of surfactant molecules, all right, you can easily control, right, the dimensionality, one-dimensional or two-dimensional within this nanocrystalline dimension, all right, and also you can control size and shape when you want to have a particular rod or wire or anything, any of nano dimensions. And also you can coat it appropriately on different things, especially for bio-related applications, biomedical applications or biomolecular nano particles preparations, right? These surfactants play a major role. Okay. Now I try to come for specific material preparations using these wet chemical processes. Right. This is a classic paper which has been presented by Murray et al. For the synthesis of cadmium sulfide or cadmium chalcogenides in semiconductor form. They have used a rapid injection process and using top triacryl phosphine or top C triacryl phosphine selenide as coordinating solvents or surfactants. And this process, wet chemical process, I need to explain it later in the subsequent slides, uses the short burst of homogeneous nucleation, right? I just understand this point. I try to explain why you need burst of homogeneous nucleation instead of slow homogeneous nucleation. And also, all right, these solvents allow you gentle growth, slow growth, so that you optimize the sizes. And also you can have some kind of recrystallization or processing, all right, to select size-selective precipitation using solvents. I try to explain in detail in subsequent slides, but still, these three things, all right, gives you control of shape, size, as well as growth within the surfactants, not going for agglomeration or other greater size of the particles. Okay, so you should control the nucleation with the burst of nucleation, and you would allow slow growth and control the growth, and also you should use some kind of solvents, right, for precipitating the sizes. This is again another paper, recent paper which discusses the chemical process in a great review. This is again injection of not a cold solution into a hot liquid. I try to explain this also in the subsequent slide. What happens when you have a precursor and injection of hot solution or a salt solution? So first you try to optimize hot surfactants, and then you try to introduce the precursors at room temperature, and leads to instantaneous nucleation. This is a kind of burst nucleation, which gives you uniform sizes and also allows you to control that nucleation without going for a larger size within the nano dimensions. And also this slow room temperature injection to the heart, right, makes you nano crystal formations, nanoparticle formation at lower temperature compared to these higher temperatures. So this hot injection method and hot probe methods out of this heater method, right? Hot injection method is a method wherein you prepare a solvent or the surfactant to a hot temperature, which will be close to its boiling temperature, and the precursors, whether at room temperature or at cold temperature, they are introduced at the hot coordinating solvent, so that you create a burst of nucleation, not a slow nucleation, burst of nucleation, so which leads to nucleation instantaneously and gives you a size control for the preparation of nanoparticles. And most importantly, it is monodisperse. It is not polydisperse when you use this burst of nucleation process. This during the nucleation process, it controls the concentration of the precursor easily when you have hot solvent or hot surfactant and introduction of precursors at cold conditions. Okay, so you try to use a heating mandel with 3-neck flask, right? What is this? Is a condenser unit, and you try to keep whatever surfactant or the solvent, and you try to heat it. All right, try to introduce the precursor solution through one arm. Sometimes part of the precursor solutions will be within this surfactant, and part if you are going for 2-component or 3-component or multi-component system, right? Some components are introduced with the surfactant itself, and 1 or 2 components through one arm of the 3-neck flask, and the other neck we usually keep in the nitrogen atmosphere, because to avoid oxidation of the metals which we try to prepare through this hot injection process. So usually one arm there will be supply of nitrogen in and nitrogen out, and then we try to condense everything using the condenser unit and try to supply the precursor through one of the 3-neck flask. And this surfactant or coordinating solvent is kept inside the 3-neck flask and heated. So this hot solution and then cold, where we inject this to make a hot injection. So the nucleation we try to control with the burst nucleation, and the growth, slow growth, try to control within the surfactant volume. Okay, so this gives you kind of control of size and shape as well as selectivity. But selectivity you can do by the other route also. I try to explain in the next slides. So you create very good nucleation all right, bursts of nucleation, nucleation at instantaneously, all nucleation. There is no way that they can go for agglomeration, and then these precipitates are isolated using some kind of solvents, right? The process is just like recrystallization, and then whatever nano crystals and nanoparticles or nano rods, whatever you prepare, right, are centrifuged, isolated using centrifugation, and then removed for further application. Okay. This monodisperse nanoparticles, size selectivity, idea is that you have a surfactant, art surfactant, you try to pour in cold precursors, and you make art solution. With aging, right, you create particles, right? These particles, right, though you try to restrict using bus nucleation and surfactants, right, sometimes there will be different size of the particles, right? You have to select or the equal sized particles to for any applications, right? So it should be of mono dispersed particles, right? Which you can do it by making use of some kind of solvents, usually propanol, ethanol, or some low alcohols, right? With a conventional, it's similar to conventional recrystallization process, right? You have prepared this with the different sizes, add poor solvent. So this is in a good solvent. So you add poor solvent so that you induce precipitation of larger sizes, and then by centrifugation you can collect it. You try to repeat the procedure by adding more and more poor solvent so that you can induce precipitation of different size of the particles. You can select the sizes by centrifuging and collecting with addition of poor solvent. So you try to prepare, right, the surfactant in a good solvent, this nanoparticles in a surfactant, and then slowly adding poor solvent, right, compared to this good solvent, and making centrifugation, right, you can select the sizes, right, in the hot injection process. So as I said earlier, there are two different categories of this thermal thing, either hot injection or heater methods. This hot injection is the predominantly used method out of this hot injection and heater methods, because hot injection you can control the nucleation and the growth, and heat up, but you can have a large scale production compared to hot injection process. So you try to, this hot injection technique produces highly supersaturated condition for the rapid injection of a precursor into hot surfactant solution, so that it controls the nucleation, right, and also the monomer concentration, right, and also controls the growth, right. In the heat up, right, you prepare the batch of the precursors and the reagents and the solvents, right, at low temperature, and heat it closer to the boiling temperature of a surfactant, all right, and again you have to centrifuge it to have the size selectivity, so that you can have large scale production of the thing. The controlling of size here is a little bit difficult compared to hot injection process. I try to come for our work, which we try to do, we did at our center, Crystal Growth Center. This is synthesis of cadmium selenide, right? We did take precursors of cadmium chloride, sodium telluride, in triglycolic acid, thioglycolic acid, which is a surfactant and solvent, right? First, you take this cadmium chloride and thioglycolic acid and into the 3-neck flask and swivel. And one of the arms, as I said earlier, we try to supply nitrogen with gas supply, and then heating that to close to 100 degrees, right, wherein we try to introduce selenium, which has been already dissolved in thioglycolic acid, as a slow through another arm syringe, right. So we try to create a formation of cadmium selenide by burst nucleation, and then we try to reflex it to get different size nanoparticles, centrifuge it, and reflex it. Okay, but whatever we get it is cadmium selenide in thioglycolic acid. So in a similar way, we did prepare cadmium telluride. The precursor sources are different here. which is cadmium chloride. You can have a chloride source, sulfate source, nitrate source, or acetate source, but the controlling the reaction is better with chloride or sulfate compared to nitrate or acetates for metals, cadmium thing. For chalcogenides, either you can have in the oxide form, telluric oxide or selenium oxide, or in the telluric acid or sulfuric acid or sodium thiosulfate or thiourea for sulfur, right? So you can have different sources for sulfur or selenium or tellurium, but each source has its own advantages and disadvantages. But in the present work, right, we take cadmium chloride as a cadmium source and potassium telluride as a tellurium source. So usually we try to use sodium telluride, but in this case, instead of sodium hydroxide, we have used potassium hydroxide for adjusting pH. So we have used potassium telluride as a tellurium source. And surfactants, we did use 3 different surfactants independently: mercaptoacetic acid, mercaptopropionic acid, to mercaptoethanol. And as said earlier, we did use 3-neck flask with condenser, and all the experiments we did only with nitrogen gas. And after preparation of nanoparticles as a poor solvent, we did use 2-propanol and then centrifuge powders from the surfactants, and then we wash with acetone to get the powders. Okay, so simply we need to use a 3-neck flask with precursors, nitrogen on one arm, and tellurium precursors from the other arm. Cadmium is with the surfactants, which is close to boiling temperature around 230 degrees for mercaptopropionic acid, and a lesser temperature for mercaptoacetic and mercaptoethanol, around 170 or 180 degrees. Okay, and tellurium and independent surfactants are purged through another arm once this solution is set up. And also, we prepared this cadmium telluride using the same procedure which we used for size-selected cadmium telluride. This is with the normal light, and this is with the UV light. The average size of the particle which we went for cadmium telluride is around 3 to 3.5 nanometer. So this is the TEM of cadmium telluride nanoparticles prepared through thioglycolic acid as solvent, and then 2-propanol and acetone are used as power. So this is classic where you have different, one can try with the thiol components, and we can try different, either small chain or long chain or surfactants, and the surfactants has its own advantages and disadvantages. You can tailor the material which you want to do using this surface tuning of surfactants, smaller size or larger size, good conductivity, or you want to have insulating, whatever medium you want to have, you can select the different functional groups for surface tuning as surfactants. As I explained earlier, we try to make different chemical processes. This is one of the classic chemical process we call it. In the chemistry, they call it as a phase transfer. Right? We prepared this cadmium selenide using normal thioglycolic acid, and we have used this for our applications. When thioglycolic acid is a surfactant, right, we are getting the conductivity value very low. So we thought of transferring this cadmium selenide to another surfactant or the coordinating solvent. Right, we have used dodecanthiol DDT, 1-DDT, right, and then we use the chemical process of phase transfer, right. So we transferred whatever cadmium selenide, right, in the triglycolic acid, right, we transferred to cadmium selenide into dodecanthiol, right. The process is very simple, right. You just add 1 or 2 drops of acetone over this cadmium selenide dissolved in or with surfactant TGA, and then add DDDT, dodecanthiol, just stirring or shaking for 20 to 25 minutes, right? Whatever cadmium selenide particles in the bottom with triglycolic acid as surfactant has been transferred to dodecanthiol here, right? This is triglycolic acid. So this transfer, right, we try to carry out by a process called phase transfer, cadmium selenide from one solvent or one surfactant to the other surfactant. This dodecanthiol you can easily remove, and the conductivity is good for this dodecanthiol. Okay. This is about chalcogenides. We also prepared oxides, titanium oxide, using the same hot injection process, right? For which we have taken titanium tetraisopropoxide as a precursor and oleic acid as the surfactant, right? We try to have the reaction like this, right? You just reflux this oleic acid with nitrogen and heat it to close to its boiling temperature. Add this titanium tetrapropoxide. We try to form titanium oleate, and then we try to add additive, right, trimethylamino anaxide with water, all right, and reflux it at 110 degrees, right? So which gives you solution or thing like this, and then we try to filter it out and make titanium oxide nanomer, right? The process goes like this, all right? So this is the flow chart for the process. This oleic acid is solvent or capping agent, so which has a structure like this long chain, and this titanium tetraisopropoxide is a titanium source, and this trimethylamino oxide dihydrate is a base for polycondensation, right, which creates the precipitation of titanium oxide. So essentially, so this milk-like solution, right? Once you make it precipitate, it gives you rods and the substrates, glass substrate, whatever substrates you want to have, right? This titanium oxide nano rods, right? Uniformly distributed, right? Uniform size nano rods, right? Aspect ratio is very, very small, but still rod like titanium oxide. Again, this titanium oxide nano rods with oleic acid is not useful for us when I will go for dye-sensitized solar cells using this titanium oxide nanorods. So we did make Ligand exchange process to have this titanium nanorods, which are surfactant the oleic acid, right, into a chloroform or a pyridine, right? So this titanium oxide with oleic acid, try to mix with ethanol of equal volume, and then we try to stir it vigorously, then which gives you precipitation of particles. These particles are centrifuged and washed with ethanol. Now, right, you add chloroform, right? This chloroform, this titanium oxide nanorods will be dispersed in a chloroform. Chloroform is small chain, so which can be useful for application in any dye-sensitized solar cells or other applications. All right. So similarly, we also made Ligand exchange using pyridine by refluxing at higher temperature, 80 degrees, not at room temperature. This oleic acid capped titanium oxide nanorods in a similar process are refluxed at 80 degrees in pyridine, so that the capping of long chain is removed, and we try to have a smaller pyridine, so which easily gives you very good conductivity compared to this titanium oxide capped with oleic acid. So this we also made some kind of precipitation or co-sensitization with cadmium selenide. I try to come on the last part with the cadmium sulfide, cadmium selenide, but the properties doesn't change. So these are all the nanorods prepared using this hot injection process, titanium oxide. So in a similar way, we have prepared copper indium sulfide, copper indium selenide using the hot injection process. And during the processes, we have used oleolamine, oleic acid as dodecanthiol as solvents, right? Similar 3-neck flask, right? 1 neck for nitrogen gas. This In this, as I said earlier, we have used cationic precursors. For example, for copper indium sulfide, we mixed copper source, indium source into the solvent, for example, polyelamine, or copper indium oleic acid, copper source, indium source in Untitled. And then we have added the anionic precursor sulfur with polyelamine or oleic acid, right, through this other arm. So this is heated to reflexing around 152 or 200 degrees, and then this sulfur is added slowly through the other arm, right? So this makes a kind of network with the cationic processes. Once you add the cold thing, which gives you the burst nucleation, and you create nucleation, burst nucleation, and then nanocrystal formation. All right. So based on this surfactants, we are able to get different structures. For example, with oleolamine, we are able to get disc-like structure for copper indium sulfide. With oleic acid, rod-like thing for copper indium sulfide. And with decanthial, all right, which is again a surfactant, right? So this is a kind of quadratic molecules, right? Particles. The dimensions we have given here 2 nanometers. This is 5 nanometer and 5 nanometers. So based on the surfactants and the process, right, you can select the sizes and the shapes. So this is for copper indium sulfide. And then we have developed different chalcogenides, copper, zinc tin sulfide, and selenide, for different applications. Right, this is the process sequence which we have used for preparation of copper, zinc tin sulfide. The sources we have used copper chloride, zinc acetate, tin chloride, and anionic precursor is sulfur powder. Right, the surfactants we have used either individual surfactants or a mixture of different surfactants. Right, I have to explain what this is. We got it for each and every surfactants. This preparation of copper, zinc, tin sulfide, though we can get it compound, the stoichiometric preparation of copper Cu is then SnS4. It's not so easy, right? So you have to be more careful with this is the system which we have used to prepare this CZTS. We have to be more careful with the reaction scheme, right? So why we mix copper, tin, and zinc into the solvent? Oleolamine or oleic acid or decanthial is that, right? We want to initiate the reaction first with copper, tin, and then with the zinc, right? So that we try to have a stoichiometry of copper, zinc, tin sulfide, right? So initially degassing with nitrogen to remove moisture and to remove whatever oxygen in the system, all right? Try to heat oleolamine to its close to boiling point, right? With copper source, tin source, and zinc source, and then finally add the chalcogen, right, through another neck, right, with oleolamine. Right, the reaction proceeds like this. Right, first copper react with thiol once you inject sulfur, which forms copper Cu2 minus X, and then tin slowly diffuse it into the copper sulfide to form copper tin sulfide, and finally the zinc diffuse into copper tin sulfide to have copper zinc tin sulfide compound in stoichiometry. Right, this compositional difficulty is due to slow solubility product of copper sulfide, which is very, very slow. The solubility is very slow in oleolamine, and also this is very slow when you make compound copper zinc tin sulfide in oleolamine. And so you have to form copper sulfide first, and then proceed with tin and zinc diffusion into copper sulfide, so that you can have copper zinc tin sulfide as a stoichiometric compound. So for that reason only, you add the precursor with the solvent, right? Copper, tin, zinc into the 3-neck flask before injecting sulfur. So this is the flow chart again for the copper and zinc tin sulfide, right? Copper chloride, zinc acetate, tin chloride, and oleolamine, and then heat to close to boiling temperature of oleolamine, and then inject sulfur with oleolamine, and then heating the mixture to initiate the first nucleation, and then adding isopropanol for centrifugation and removing and take it into the powder form. Again, this oleolamine is a long chain. All right, you have to make a smaller chain polymers over surfactants for any applications. Right, I try to come to this part in a short while. So we also made a ligand exchange for this CZTS, and also we made it as a powder form by centrifuging with propanol and then washing with ethanol and then drying. Right, we made stoichiometric copper zinc tin sulfide powder for further applications. As I said, we have used independently as well as mixture of surfactants for pure oleolamine. All right, you can see the structure of this is SEM micrograph. All right, structure of copper zinc tin sulfide, and then with oleolamine and one octadecene. Right, this is a mixture of two surfactants. You can see the change of surface morphology. And similarly, from oleolamine and oleic acid mixture, 1:1, right? You see the change closer to plate-like structure with oleic acid and one octadecene, right? It goes to needle-like structure. And pure oleic acid, it goes entirely needle-like structure. This is true in different magnification of the same oleic acid surfactant for copper zinc tin sulfide compound. With pure 1-dodecanyl, again it goes as a particle thing. So overall, for different mixtures or independent surfactants, right? The results is that with oleolamine, we get nanoparticles with irregular structures. With oleolamine and a mixture of one octadecene, right, nearly spherical, but with some agglomeration. When you have oleolamine, oleic acid, or oleic acid, one octadecene, right, as surfactants, right, you get nanoplate-like structures. With pure oleic acid, we get nano flower-like structure with needles. Most of the thing is in needles. And for 1-dodecanyl as a pure surfactant, we get spherical shaped particles with agglomeration. So different solvents or different solvent mixtures, right? You have different shapes. And also you can select the sizes when you filter it out with the proper solvents. And then we are able to prepare the CSTS in the ink form also, the same procedure, right? When you remove the supernatant, right, we try to dissolve in a chloroform to make it an ink, and we try to use it for further applications. The solvent we use for this process is oleic acid solvent, or surfactant is oleic acid, right? This is copper zinc tin sulfide. In a similar way, we have prepared copper zinc tin selenide, right? Of sulfur and oleic acid, we have used selenium in oleic acid, and we have prepared CZSE, right? Copper zinc tin selenide, again in the ink form. All right. So we have used oleic acid as surfactant, and finally chloroform as solvent. As like sulfide, right? Similarly, selenide has the same nature of evolution of morphology with different solvents or surfactant mixtures. Okay. Yes. As I said, I explained earlier, when we make some kind of ligand exchange or phase transfer, right? So we make whatever properties of the surfactants in a different way. For example, we have prepared oleic acid surfactant CZTS, or oleolamine as surfactant CZTS, which is hydrophobic in nature, and we try to make solvent exchange with toluene, and then we try to give a treatment called ammonium sulfide formamide treatment, which gives you a ligand exchange process, right? Whatever oleic acid or oleolamine, and the surface has been removed, and small molecules are added onto the surface. Now the whole CZDS become, after ligand exchange, become hydrophilic. Right? So we can change the surface properties of the nanoparticle from hydrophobic to hydrophilic by simple this ligand exchange process. Okay, you can see the surface morphology and other characteristics of the molecule. After this is pure oleic acid and oleolamine and CZTS nano particles without ligand exchange. You can see the particle evolution after ligand exchange. So this is hydrophobic with oleic acid and oleolamine. After ligand exchange with toluene or chloroform, right, it becomes hydrophilic, and it has got very good applications. When we have tried with the photocatalytic applications, right, with methylene blue and rhodamine B, you can see the evolution of cleaning with respect to, this is for methylene blue, CZTS after ligand exchange, all right, before degradation, all right, with direct sunlight, right, addition of CZTS, hydrophilic CZTS with direct sunlight, you can see the degradation of methylene blue. Similarly, rhodamine B also, right? So this is almost 85% to 90%. This is around 70% degradation with CZTS converted after ligand exchange, which makes you hydrophilic, and then used for photocatalytic reaction with rhodamine B. We have checked with direct textile effluent also, which with textile industries, right? We got around 50% degradation. Still, the stoichiometry as well as other properties has to be adjusted for CZTS, so that we can have better photo degradation for this commercial textile and other effluents. Okay, so this degradation or photocatalytic reaction you can have only for hydrophilic CZTS after a ligand exchange, not with hydrophobic CZTS, which comes before ligand exchange. In a similar way, we have prepared many other compounds. This is one of the classic compound which is useful in dye-sensitized solar cell as counter-electrode. It's copper sulfide, which comes in 4 different structures, polymers. So we have prepared Cu2S as well as Cu-S2, right, by this hot injection reaction. And again, we have used different surfactants, oleolamine, oleic acid, octadiezen, and undocanthiol. And we are able to get a very good evolution of this digenite phase of copper sulfide after centrifuging with isopropanol and ethanol, and then finally dispersed in chloroform or NXA. So as an ink, this is surface evolution with oleic acid for copper Cu2S, right, almost particle size thing, and also we are able to get disc-like thing for oleolamine octadiezen mixture for surfactants. This is for oleolamine and oleic acid mixture, which was a particle, the same copper sulfide, all right, and a mixture of oleic acid, octadiezen, and dodecanthiol gives you 2 different mixture of phases, right, copper sulfide and Cu2S, and the particle evolution is almost spherical. Okay, and then finally we are also able to get disc with pure dodecanthiol or the same CuXS nanoparticles. The important parameters which play a key role in this evolution are surfactant, time, and temperatures. The surfactants control the shapes and size in the solution phase synthesis. All right, this oleolamine, when it is used, it prevents the faceted growth and influences the size control. And 1-dodecanthiol and oleic acid, right, evolves the facets unlike oleolamine and gives you nano disk. So the overall kinetics of evolution of size and shape rise with surfactants, and with time, right, you can control the agglomeration and restrict thing, and temperature. So you should be closer to a boiling temperature of the surfactant, but it should not be more than boiling temperature of the surfactant, and also the solution which add through the other arm, which will be cold, not like hot, and then at what temperature you initiate the growth is also an important parameter. So the surfactants, time, temperature, when you identify the proper solvent, right, decides the evolution of shape and selectivity of the sizes. And also we have tried the same copper sulfide nanoparticles with different mixtures, right, in thin film form as well as with reduced graphene oxide for different applications. We have, and for this is copper oxide. Previously we did make with the chloroform and NXA, now dissolved in chloroform with acetonitrile treatment, right? You can see the evolution of nanorod like, which we have dispersed or made a composite with RGO, reduced graphene oxide, right, for solar cell applications. We have prepared this ink, and then we made the thin film. This is RGO or CUS as counter electrode for dye-sensitized solar cell, and then we made this as an ink, and then deposited and spread by a spin coating process, as well as we have used thermal evaporated copper sulfide to control the size, right? We have compared both the results, right? This is for thermal evaporated, and then the ink on substrate. So almost is two different magnifications, right? The properties are similar. So it gives you very good compactness for the nanoparticles. Right, this is simple copper sulfide thin film. This is nano composites with RGO. We can see the surface roughness is close to nanometers, 28 nanometer. When you add composites, right, it is close to 100 nanometers. And we have also prepared copper indium sulfide, zinc sulfide, again for solar cell application as electrode, counter electrode, and dye-sensitized solar cell with the precursors, right? Zinc acetate, copper iodide, indium acetate, with a mixture of 1-octadecene and oleic acid as surfactants. And the whole thing, right? We did under vacuum, not in nitrogen atmosphere, right? And then octadecene is injected at 230 degrees to create burst of reaction, and also we did quench it to toluene so that we can avoid agglomeration, and then the treated particles are centrifuged with ethanol or toluene, and then finally dispersed in chloroform to make it ink, and then for further applications. Then this is the most interesting art injection process being used for preparation of perovskites, mainly methyl ammonium lead iodide. Usually in literature they use either a one-step process or a two-step process. All right. Initially they try to prepare methyl ammonium iodide, and then they mix it with lead iodide in DMF or DMSO with a surfactant, right? And finally, they try to get methyl ammonium lead iodide. We also made a similar process, everything in a glow box, all right? We did use one-step as well as two-step solution processing, but in addition to that, we have tried a single-step vapor process also by using two different sources and a single substrate process, right, by evaporating methyl ammonium iodide and lead iodide on different substrates. So compared to this one-step solution process, this two-step process give better results, but still the results moisture incorporation and oxidation avoided the quality of the films we prepared on the substrates. So this is a actual flow chart which we have used. We have taken methylamine and made hydrochloric acid 57.8%, 33.8%, and solution we have prepared methyl ammonium iodide or bromide. Then we have added lead iodide subsequently from other arm, and we also made the ink from there, and then finally made the film in a glow box. When we used pure methyl ammonium lead iodide ink over the substrate, right, we always end up with some kind of problem with the stability, and we have used 4-distributyl as a coating or additive layer before going for annealing or making other arms over perovskite layer. So you try to coat the perovskite layer. Over the perovskite layer, there is another layer which is an encapsulant layer made of 4-distributyl, which avoids the moisture going in contact with the perovskite layer and safeguards the perovskite layer from oxidation or any degradation. So this is the kind of layer. Everything structurally it goes close to nanometer, but to avoid degradation, we have used this 4-distributyl and to go for further device development. And we have also prepared cesium based perovskites. Right? This is again by 3-neck flask. The precursor we have taken, and the thing is cesium carbonate with different surfactants. I try to come on the next slide how one can play with the different surfactants as well as preparation of different halides. Okay, this is cesium carbonate in 1 after deposition or oleolamine with oleic acid mixture heated to close to melting temperature or boiling temperature of oleic acid, which is 150 degree, and then slowly lead iodide or lead bromide is added onto the other arm. Okay, so this is next step, which forms cesium oleolate. So lead iodide in 1 after deposition or oleic acid, right, slowly added. It is heated up to 2 degrees to initiate the burst nucleation, right? Quench it fast. You try to get quantum dots of whatever halides you put into the other one, chloride or bromide or iodide. Okay. So this is cesium lead. So in the similar way, you can prepare cesium tin as well as cesium germanium halides, but its preparation is easier for cesium lead and cesium tin. It is very, very complicated for cesium germanium halide layers. Right. So once you have some kind of flowchart here, I have given here. If you have prepared cesium lead bromide, right, you can add after design with iodine, right, you can convert it to cesium lead iodide, right. In a similar way, right, if you have cesium lead iodide, you add tetrabutyl alcohol with bromine, right, you can convert it into cesium lead bromide, but the reverse reaction is not possible, right. Similar way, you can play with different halides of cesium lead, cesium tin, right. You can, once you have cesium lead iodide, you can prepare cesium lead bromide and then cesium lead chloride. Similarly, you can play with this, right. All these halides find application in luminescent as well as solar cell applications. Also, you can use this hot injection with 2 different co-sensitization, and we have tried with cadmium sulfide, cadmium selenide, titanium oxide, copper indium sulfide. We are able to prepare different structures, right? So this is with titanium oxide nanotubes filled with cadmium sulfide or cadmium selenide, and then add the other one. If you have cadmium sulfide filled with titanium oxide, you add cadmium selenide and go for some structure tandem devices, all right? So this is the idea, right? You try to get the absorption of 1.7 electron volt by cadmium selenide, 2.25 for cadmium sulfide, 3.2 for titanium oxide as an absorber layer, right? You can harvest more science energy and you can improve the efficiency, right? This is co-sensitization with different nanoparticles, right? The same hot injection process, okay? Okay, the next, so far I have discussed detail about the wet chemical process and what are the materials we have studied using this surfactant based analysis, right, from chalcogenides to oxides, right? And now I have the electrochemical process, right, which again used for prepare many nano particles or nano structures of different dimensions. I try to give insight on electrolysis initially, 1 or 2 slides, and then different aspects of electrochemical I try to explain in the latter part. This is very simple process wherein you take an electrode, especially for this is electrolysis process, where you take an electrode of zinc, right? Just insert in a copper sulfate solution with proper reducing agent and a complexing agent, right? You can get the deposits of copper over zinc sulfate. This is a simple demo thing. The process is called electrolysis metal displacement. You are displacing some surface with some other metal surface. And in a larger scale, you can initiate a cathodic reaction and deposit on a larger area, for which you use precursor as a metal salt. For example, if you want to deposit nickel, right, you use nickel chloride as metal salt, and the reducing agent in this case is hypophosphite, right? And then you need a stabilizer because this reaction has to be controlled, all right? This is done with a catalytic poison, usually with thiourea, and then to prevent free metallization of nickel, right, you need a complexing agent to, right? You need a stabilizer and also you need a controlling agent, complexing agent, and then to keep the pH, you need a buffer. And though it has to be stabilized, and also you have to avoid instability, so you have to increase the inclination rate, which you need accelerator, usually pyridine or diluted acid. All right. So the process is that you take the reactants, all right, just insert the electrode, whatever electrode you want, put in, the deposits take place. For example, if you want to have nickel deposits, right, you have nickel chloride, hypophosphite, a stabilizer, complexing agent, and an accelerator into the solution as electrolyte, and then nickel gets deposited into whatever electrode you have connecting medium. So this is electrolysis deposition. You didn't supply any electric current or potential, right? Just with the electric electrolysis within the salt, right? The metal gets deposited, right? This electrolysis deposition is controlled by a reaction scheme called Evans diagram, right? You have anodic polarization and a cathodic polarization. This metal always goes as a cathodic polarization and is controlled by hypophosphite, which is anodic polarization. And the mass of deposits you can calculate using the relationship ITM divided by F and Z. I is the current of deposition, which is area of the electrode, where you get a lot of electrode deposits, and the I current of deposition, and then T is the time of deposition time, M is the molecular weight of the material which you are getting deposits, right? F is the periodic constant, Z is the charge of the ion, right? In this case, nickel 2+. So in a simple way, in an electrolysis deposition, if you control the reaction with this metal salt, reducing agent, stabilizer, complexing agent, buffer, and accelerator, you can get metals deposited onto any electrode. All right. But in a controlled way, right, you can do with an electrochemical process rather than with electrolysis process, right? This electrochemical process you can do several ways. right? The simple way is electrochemical deposition with quasi two-dimensional geometry, and then electrochemical deposition of three electrode geometry or thin films. And the nanostructures, right? Using these two, right, we can get nanostructures by optimizing some parameters, right? These nanostructures you can either get with an active template assisted electrode deposition or restrictive template assisted electrode deposition. So overall, everything you try to get by electrochemical process. In a two-dimensional geometry, just consider this as a glass plate. This is a glass plate. This is a microscope on the surface of the glass plate. There is a wire, right? For example, copper wire. This is copper wire, right? You get a connection to the copper wire. You keep the copper sulfate solution, all right? This is anode and this is cathode. So this copper metal deposit on the cathode. Once you see from the top, right, you can see some kind of a network of fractals or wires. The two-dimensional diagram looks like this. So this is electrode, cathode, all right. This deposits from the electrode. So in this way, so this everything is nanostructure, but it's not a controlled one. But you can get any metal using this simple two-dimensional geometry. So you have two electrodes as wires, and you connect it to some kind of power supply. But it's a crude way. It's not a controlled way. But in any case, you can get very good nanostructures, right? So you have an electrolyte with a particular distance between these electrodes, right, and the glass plates, right? You try to get nanostructures between these two electrodes. So you can change the electrolytic conditions and other things. You can optimize the nature of nanostructures. Okay, this is very, very simple, crude way of preparing nanostructure. Near two electrode geometry. All right. So this is one of the conventional way for three electrode geometry. Prepare again any nanostructure using this. So you have a bath, electrolytic bath. You have an anode, a cathode connected to the power supply. All right. For a simple example, again I try to explain with copper. Right. You have copper sulfate as a electrolyte. Right. Just apply current or voltage in between the electrodes, and usually it will have a three electrode geometry. All right. There will be a reference electrode close to anode, but as a two-dimensional figure, I have shown only these two. Okay, so once you apply, right, depending on the electrochemical reactions within the electrolyte and distance between the electrodes and other parameters, you have a deposition of these metallic structures on the cathode and evolution of oxygen or some gases at the anode. Suppose if there are some kind of oxides, right, there will be the deposition of oxides at the anode. Right, most of the reactions, metal reactions, right, they are reducing reactions which will occur only at the cathode. So this is where you get deposits called working electrode. The other electrode is counter electrode. Then you can have a reference electrode, usually silver chloride or saturated caramel electrode as a reference electrode, right? To measure the voltage or current applied to this three electrode geometry. So you have a reduction at the cathode and oxidation at the anode, and based on this reduction oxidation reaction, you get deposits at the cathode or anode, right, depending on the electrolyte also. So this three electrode geometry you can use configure with templates. I try to come in the next slides how one can use the template. The templates may be either metal based or polymer based, right? And the deposition conditions, right, depends on the source materials, the precursors, and the concentration, pH of the solution, temperature of the solution, and whether you apply a constant voltage, constant current, or pulses of voltage or pulses of current. If you apply constant voltage, it is potential static. If you apply constant current, this is galvanostatic. If you apply pulses of current or pulses of voltage, right, this is pulse conditions. And also this electrochemical reaction you can control with additives or supporting electrolytes and the solvents, right? The nature of solvent, you can have aqueous solvent or non-aqueous solvent. Most of the metal deposits are if you are using chloride or sulfates or nitrates or acetates, right? This is done with aqueous, so it is easy to control reactions in aqueous compared to non-aqueous depositions. And the templates, right? You can use highly oriented pyrolytic graphite as a substrate, graphite substrate with holes as a substrate. I don't explain how it is used in the subsequent slides. Aluminum foil with holes made with laser, or stainless steel grains, carbon tape, polymer-based materials, polypyrrole or polyaniline, PMMA, many polymer-based electrodes are used as templates. And finally, AAO, anodized aluminum oxide. I need to explain how to prepare anodized aluminum oxide, how it can be used as a template to prepare nano structures in a detailed way in the subsequent presentation. Okay. So this is active template process. This is dimension of template, which is used as an electrode. This is a simple graphene sheet with kinks, right? So the dimension is a millimeter, right? This height will be around micrometer or nanometer, right? So this whole setup with the steppage or kinks in the electrode is used as a working electrode in the electrode deposition process, wherein you get deposits at the kinks first, right? Once you harvest, these deposits are nano particles and nanostructures. So this is the stainless steel or polymeric plate wherein you make holes, right? These are simple holes made using laser or some other mechanisms. The holes are either micrometer dimension or less than submicron dimensions. Once used, these holes prepared sheets or templates in the electrodes, in the working electrode in the system, right? You try to get deposits closer to the holes or inside the holes, right? Once you harvest it, you get nanostructures or nanoparticles. This is again active template assisted process. Okay. In a restrictive template assisted process, this is a two-dimensional view of a three-electrode system. This is a working electrode, platinum electrode, and the reference which will be closer to platinum electrode. This is a template. Either this template, you make use of a metallic template or polymeric template or a porous membrane. And once you pass, this is an electrolyte, but once you pass electricity or voltage, right, you try to get deposits on the holes or porous sides, and you can dissolve this other part other than the porous part which are filled with nanostructures. Once you remove the other parts, you get freestanding or nanostructures on the working electrode. You can remove it. And this is most of the applications people use this restrictive template assisted electrode deposition process to prepare freestanding metal or compounds, even polymers. Right. So for this restrictive template assisted electrode deposition process, the electrodes used are mesoporous silica, mesoporous alumina, which have a membrane like porous, nano indented holes, polyethylene glycol membrane, polyvinyl pyrolinene membrane, and polypyrrole membrane, PMMA membrane, and also depending on the applications, right, you can have different metal substrates with holes. Right, whatever the thing, you try to cover the working electrode with the membrane or the template, and based on the electrolyte, right, on the application of galvanostatic or potentiostatic or pulse conditions, you try to get the deposits which are nano dimensions on the holes or pores. Try to remove the other parts using a solvent, and you can have freestanding nanostructures with a restrictive template assisted electrochemical deposition process. And this is condition how one can prepare anodized alumina membrane or structure, right? You have a electrolytic solution consisting of H2SO4 and HI, iodide, and the electrodes are aluminum, right? We apply particular voltage or current between these electrodes, right, which try to etch, right, depending on the time and the pH value, right, substrate, and try to gives you porous nature for the anodic aluminum at the anode sides. So first it tries to oxidize the aluminum on the anode side, as well as it tries to give etching portion depending on the structure, and try to prepare a membrane. When we have the reaction like this, for this electrochemical reaction, this is anodic oxidation of aluminum, so which gives you membrane's structure. So once you have this porous template, right, you can make use of this as a working electrode, and then make use of a proper electrolyte to fill the pores with whatever material you want, and you remove the other existing aluminum by etching, and then you can get freestanding wires. Right, the dimension is very, very small. This length is only in micron scale. Right, length of the pores is only in micron scale. So similarly, you can use some kind of patterning on different substrates, and these patterns you can use as a electrode, a restrictive electrode, and then make use of a freestanding nano structure by using this electrochemical process. Right, this is aluminum by thermal evaporation, and then the surface is polished using electrochemical polishing by using anodization of this aluminum. Right, you get alumina pores, right, with selective etching, and then filling proper thing. You can get the nanowires, and then etch out whatever alumina outside the pores. Right, you get freestanding nanowires. So this is one kind of aluminum oxide, all right, anodized aluminum oxide, and the structure, right, like a honeycomb structure, where we have deposited cadmium telluride by using electrochemical process, cadmium chloride as cadmium source, tellurium dioxide dissolved in hydrochloric acid as tellurium source, adjusting the pH close to acidic, right, we are able to get freestanding. This is almost 2 micron thick, rather length, freestanding nanowires of thickness around 50 nanometer. This is cadmium telluride in anodic aluminum template. All right. Similarly, we can use this anodic aluminum template with the controlled dimensions and prepare carbon nanotubes. Right. I tried to come on the last part, how to prepare the carbon nanotubes, different processes, and also functionalization of carbon nanotubes and graphene on Friday. But since I tried to discuss this electrochemical process, right, I tried to give the insight on the preparation of carbon nanotubes using anodized alumina as template and using catalyst reactions. This catalyst usually is again some kind of hydrazine-based catalyst. Okay, and also using carbon monoxide, you can prepare single-walled carbon nanotubes. This is again titanium oxide, like anodic alumina. Titanium oxide we can prepare as nanotube using anodization. Right. In this, instead of aluminum, right, here for the anode, right, it is taken as titanium. Yeah, so anode is titanium, and cathode is platinum, and the reaction is done with ethyl alcohol, and yeah, ethylene glycol, ethylene glycol 97%, and water 2% with HF 1%. Right, this is titanium anode, and the potential we apply is very high. In this case, we have applied almost 20 volts, right, in between 1 centimeter electrode system, very high potential. Right, we try to etch out whatever oxidized part, and we try to get freestanding titanium oxide nanotubes. So these two different dimensions. This is with ethylene glycol 97% and time of 10 hours, and time of 15 hours, right, diameter, still large diameter, 100 to 130 nanometer diameter of tube. Both anodization process, right? This is for 10 hours and this is for 15 hours, right? By increasing the time, right, you increase the diameter of a tube. Also, the pore length or height you can improve by increasing the time as well as with the voltage you apply. In both the cases, the voltage is very high, 20 volts. So this is expanded part of titanium oxide nanotubes, anodized titanium oxide nanotubes. So you can have either metals, metal sulfides, metal chalcogenides, or any compounds which will get you a reduction thing in the working electrode. You can prepare in the working electrode. Most of the oxides, zinc oxide, alumina, or titanium oxide, almost all the oxides you prepare. It's an anodized reaction. So anodized part, titanium oxide on the anodized part, and aluminum oxide on the anodized part, as well as zinc oxide. You can prepare in a similar way as an anodized part. So oxides on the anodes, and most of the compounds which should come out around the reduction reaction, right? They are the cathodes or as working electrodes. We can prepare using electrochemical deposition process. The same surfactants you can use in electrochemical deposition also. The most predominantly used surfactant is common name AOT, titan oxide, which forms a micelle like thing, and then so this forms a working electrode, and then you can deposit through the holes of the thing and remove the micelle. You can get a freestanding compound or metal by electrochemical process. So the process is that formation of cylindrical micelle and then deposition of by electrochemical process, which this micelle is attached to the electrode as a working electrode, and then you try to deposit by electrochemical process and remove the surfactant with appropriate solvent. You can freestanding deposits. And also, as I said, reactive electrodes, you can have different electrode, polymeric or metallic, right? This is one such electrode which was used using sputtering titanium and gold, which are as well as the PMMA, and then finally gold cubes, nano cubes, has been electro deposited for some application in electronic industries. Right? So the process is spin coat, reactive ion, then UV curing, then reactive ion etching, then gold sputtering, and removal of the template, and you get gold cubes. Right? The deposition is done, gold deposition is done using electrochemical process. Okay. On the conducting substrates. So the special case of this electrochemical process is electrospinning. Though it is an entirely different process, but it also comes as an electrochemical process. All right. This electrospinning is very much used for all kinds of preparation of fibers using nanofibers, using this electrospinning process. Wherever you want to have a fiber in the nano dimension for application, right? This is easier as well as appropriate to go for an electrospinning process. The experimental arrangement is so simple that you have a syringe, all right? This is a syringe, and the needle of the syringe is attached to one end of needle of the syringe is one end of the power supply, and there is a collector. Usually, it will be plate collector or drum collector, right? Both of the cases, right? You correct the collector to the other end of the power supply. So you have a power supply connection to the needle as well as the collector, and then the syringe, right, filled with polymeric solution, and the syringe movement is controlled with a controller, right? You can make the syringe as a reservoir and pile the polymeric solution slowly depending on the movement or control of the controller. right? You can spray very fast or slow through the needle using this controller, right? So once you have power supply, right, between this needle and the collector, all right, once you spray the polymeric solution, because of this electric field in between these two, right, the solution with the whatever material you have, right, sprays comes as a fiber and is collected with the collector, right? The fiber length or fiber quality depends on the distance between this needle and the collector, as well as the concentration of the solution in the polymer and whatever additive agents you have taken into the syringe and the application of the field. Here again, the field is not so simple. It goes to kilovolts. Simply, it goes to kilovolts, right? For normal fiber, it goes to 10 kilovolts. It goes up to 25 to 30 kilovolts of power supply, and the length or the distance between this needle and the collector goes from few centimeters to either 2 to 3 centimeters to even to 50 centimeters, depending upon again on the solution and the fiber you want to make as in a nano form, right? So the reservoir with polymer solution, you try to spray the solution, right, because of the high voltage between the collector and the needle, right, it is getting as a fibrous thing. So slowly it comes to the collector, right. Once you draw the syringe, right, it comes out as a fiber. Okay, so this is a plate collector. If you have a drum, right, the drum will be rotated, the fiber will be collected in the drum as a rotated fiber. Okay, so this is a sample of the fiber which comes from the plate collector, and this is the SEM diagram of the fiber. So this fluid pumping, right, you control with the controller with the automatic syringe, and the positively charged voltage which goes to kilovolts, right, you can control with the voltage supply. Though it looks like a simple thing, right, it's not so simple. You have to optimize and you have to get proper fibrous nature, whatever solution you spray, and you just get deposited onto the collector. Okay, but it's very good instrument. You can get very good fibers of polymers, metallic, or compounds for many applications, mainly bio related applications. Okay, even core shell structures has been attempted using this fiber, two different syringe structures, core shell. This is the drum collector, wherein this is sprayed, right? So drum collects, rotates, so it's collected. So it's sprayed, the drum rotates, right? So the fiber is collected onto the drum. Depending on the collector, you can have either random fibers or aligned fibers, and you can optimize the distance, application of voltage or current, and also the concentration of the precursor solution to optimize the random structure or the aligned structure. So this is one of the recent results where they are able to get core shell for photoluminescence. This is again bio-related application for fibers, right? Thick fibers wounded on base also got a very good application for biomedical field. In addition, now recent days from agricultural universities, right, this electro spinning process has been used to prepare external fibers using the solution of banana stem, right? And this is made as fiber and wound around banana or mango or other fruits to safeguard the fruits, right? To improve the shelf life of the fruits. And this is very much used in agricultural university or agricultural area, right? So this is a report, right? This is raw thing, the shelf life, right? This is a wounded thing. The wounded, this fiber wounded thing improved the shelf life of the fruits. The idea is like this, right? They make the banana stem solution, right? Spin it, make fiber, and then load it on fruits as fiber. Okay, a banana or mango or whatever thing. This fiber is wounded using electro spun technique.